This episode is brought to you by Cisco Educational Premium. On our last episode, we introduced ourselves to the Planck scale. We saw how the Planck scale defined the smallest units of measurement and how Planck came up with it. Today, I want us to proceed from there. Some Planck units, such as those of time and length, are many orders of magnitude too large or too small to be of practical use. So that Planck units as a system are typically only relevant to theoretical physics. In some cases, a Planck unit may suggest a limit to a range of physical quantity where present-day theories of physics apply. For example, our understanding of the Big Bang does not extend to the Planck epoch. That is, when the universe was less than 1 Planck time old. Describing the universe using the Planck epoch requires a theory of quantum gravity that will incorporate quantum effects into general relativity. Such a theory does not yet exist. Several quantities are not, and I quote, extreme in magnitude, such as the Planck mass, which is about 22 micrograms, very large in comparison with subatomic particles and within the mass range of living organisms. Similarly, the related units of energy and momentum are in the range of some everyday phenomena. Planck units have little anthropocentric arbitrariness, but do still involve some arbitrary choices in terms of the defining constants. Unlike the meter and second, which exist as base units in the SI system for historical reasons, the Planck length and Planck time are conceptually linked at a fundamental physical level. Consequently, natural units help physicists to frame questions. Frank Wilczek puts it succinctly. We see that the question is not why is gravity so feeble, but rather why is the proton's mass so small? For in natural Planck units, the strength of gravity simply is what it is, a primary quantity, while proton's mass is the tiny number 1 on 13 quintillion. While it is true that the electrostatic repulsive force between two protons alone in free space greatly exceeds the gravitational attractive forces between the same two protons, it is not about the relative strength of the two fundamental forces. From the point of view of Planck units, this is comparing apples with oranges because mass and electric charge are incommensurable quantities. Rather, the disparity of magnitude of force is a manifestation of the fact that the charge on the proton is approximately the unit charge, but the mass of the protons is far less than the unit mass. In particle physics and physical cosmology, the Planck scale is an energy scale around 1.22 times 10 raised to 19 gigafolds. The Planck energy corresponding with the energy equivalent of the Planck mass is 2.17645 times 10 raised to negative 8 kilogram, at which quantum effects of gravity become significant. At this scale, present description and theories of subatomic particle interactions in terms of quantum field theory break down and become inadequate due to the impact of the apparent non-renormalization of gravity within current theories. At the Planck scale, the strength of gravity is expected to become comparable with the other forces, and it has been theorized that all the fundamental forces are unified at that scale. But the exact mechanism of this unification remains unknown. The Planck scale is therefore the point at which the effects of quantum gravity can no longer be ignored in other fundamental interactions, where current calculations and approaches begin to break down and a means to take account of its impact is necessary. On these grounds, it has been speculated that it may be an appropriate lower limit at which a black hole could be formed by collapse. While physicists have a fairly good understanding of the other fundamental interactions of forces on the quantum level, gravity is problematic and cannot be integrated with quantum mechanics at very high energies using the usual framework of the quantum field theory. At lesser energy levels, it is usually ignored, while for energies approaching or exceeding the Planck scale, a new theory of quantum gravity is necessary. Approaches to this problem include string theory and M theory, loop quantum gravity, non-commutative geometry, and causal theory. In Big Bang cosmology, the Planck epoch or the Planck era is the earliest stage of the Big Bang before the time passed was equal to the Planck time, or approximately 10 raised to negative 43 seconds. There is no current available physical theory to describe such short times, and it is not clear in what sense the concept of time is meaningful for values smaller than the Planck time. It is generally assumed that quantum effects of gravity dominate physical interactions at this time scale. At this scale, the unified force of the standard model is assumed to be unified with gravitation. Immeasurably hot and dense, the state of the Planck epoch was succeeded by the grand unification epoch, where gravitation is separated from the unified force of the standard model, in turn followed by inflationary epoch, which ended after about 10 raised to negative 2 seconds, or about 10 raised to 11 Planck time. After the measurement of the cosmological constant in 1998, estimated at 10 raised to negative 122 in Planck units, it was noted that this is suggestively close to the reciprocal of the age of the universe squared. Barrow and Shaw proposed a modified theory in which the cosmological constant lambda is a field evolving in such a way that its value remains lambda equivalent to the age of the universe squared through the history of the universe. The Planck length, denoted Lp, is a unit of length defined as Lp is equivalent to root of reduced Planck constant G on C raised to 3. It is equal to 1.6162518 times 10 raised to negative 45 meters, where the two digits enclosed by parentheses are estimated standard error associated with the reported numerical value, or about 10 raised to negative 20 times the diameter of a proton. It can be motivated in various ways, such as considering a particle whose reduced Compton wavelength is comparable to its Schwarzschild radius. Though whether those concepts are in fact simultaneously applicable is open to debate. The same heuristic argument simultaneously motivates the Planck mass. The Planck length is a distant scale of interest in speculation about quantum gravity. The Bekenstein-Hawking entropy of a black hole is 1/4 area of its event horizon in units of Planck length squared. Since 1950s, it has been conjectured that quantum fluctuations of the space-time metric might make the familiar notion of distance inapplicable below the Planck length. This is sometimes expressed by saying that, and I quote, space-time becomes a form at the Planck scale. It is possible that the Planck length is the shortest physically measurable distance, since any attempt to investigate the possible existence of shorter distances by performing high energy collision will result in a black hole production. High energy collision, rather than splitting matter into finer pieces, would simply produce bigger black holes. The strings of string theory are modeled to be on the order of the Planck length. In theories with large extra dimensions, the Planck length calculated from the observed value of G can be smaller than the true fundamental Planck length. The Planck time, Tp, is the time required for light to travel a distance of 1 Planck length in a vacuum, which is a time interval of approximately 5.39 times 10 raised to negative 44 seconds. No current physical theory can describe time scale shorter than the Planck time, such as the earliest events after the Big Bang. Cisco Educational Premium is a section of Cisco Educationals with content that is not hosted here. There are episodes ranging from long to short videos. Remember those good old shots of ours? They are there. So do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself. And I will see you in the next episode of Cisco Educationals.